So the work I will present you today is some kind of overview of some work I've done recently, mostly in collaboration with Professor Antti Olasvirta in Aalto University, but also other collaborators like Marielle Gossain, who now left academia, unfortunately, and Aurélien Yosh, who is a postdoctoral researcher in Glasgow University. And so I will give you the reference of the paper that I present in the end of the presentation. Okay. Okay. So maybe one specificity of this presentation within this seminar and analogy is that I will use, I would say, almost the first half of the presentation not talking about analogies, but analogies will come quickly, and I think the first part is very important to get a general idea, to get the gist of what this project is about and how analogy naturally enters into this game. Okay, so the main part of the presentation will be about how to teach vocabulary using artificial intelligence, and then how to teach grammar using artificial intelligence. And so I will conclude the talk with some perspectives, depending on how much time we have left, some perspectives on how to make an even more general teacher. Okay, so let me first introduce you the problem of teaching vocabulary. So this is basically about developing a new Duolingo. So you just have a list of vocabulary, so a list of words that you would like a learner to learn. And as a teacher, you have to choose the optimal order, the optimal sequence, present these words. So a very quick remark, that if we had perfect memorization capabilities, this would be trivial because we just would have to present each word one time, and this is the end of the problem. That would be great. But unfortunately, all of you who learn a foreign language know that it's not the case, and we need repetition. And repetition, not only repetition, but repetition at optimal times. This number of repetitions highly depends on the learner. So we are all different regarding learning. That's why we need some individualization of the teaching. Individualization in terms of the presented items, and individualization in terms of the learners. Like on this example with Japanese kanjis, you can see that the left-hand side is way simpler to remember than the right-hand side. And I don't speak Japanese, so I hope it's not swear words, but I think it's not. But yes, so that's individualization needed in terms of items to present. But also learners can be quicker at memorizing than others. And so for quick learners, obviously we will not have the same teaching policy as for slower learners. Also, some other challenges for this kind of teaching are about irregular learning sessions, because the learner is taking breaks. So you will, you will learn vocabulary for 15 minutes, and then you will do something else, come back to it 6 hours later, or maybe 2 days later, or maybe 1 week later. And knowing this kind of irregularity is important to plan what you will teach. For instance, if you know that the learner is about to finish, to end a learning session, and will probably not go back to learning before 1 week, better not teach him a new word right now. Maybe it's better to revise previously seen words. So that's the kind of questions which arise from the irregularity of the learning session. And also there is this interesting question of the learner's learning objectives, because all learners don't use Duolingo for the same thing. Some, they just use it because they have an exam in 1 week and they need to learn this list of 100 words for the exam. but some others, they just want to master a language, but they're not in a hurry. So it can take a month, but they want that in a month they perfectly master the 100 words. So everyone can have a specific objective, and that's something that we should take into account. Okay, so what is done in Duolingo? Because you will say we have perfectly well-working applications, so why not use this? So basically, Duolingo-like applications are based on the heuristic approach, which is quite old, but actually which has the best results right now, which is called the Lightner System. So it's mostly it's a very heuristic approach based on some kind of boxes. So the boxes are numbered from 1 to 5 here. And so when a word is in box 1, it means that the learner does not know them at all. And then if the learner shows that they know it a bit, then the word goes to box 2. And if they show that, yeah, they know it very well, then it goes to box 3, etc. But if the learner makes a mistake on these words, then it goes back to the previous box. And the thing is that each box is associated to some frequency of presentation. And so, for instance, box 1 will be the most frequently presented words, while box 5, since it contains words that you know very well, then this box here, the words in this box will be presented less frequently. So that's the general idea of Lightner systems. And it works very well in practice. Now our approach is very different. We wanted to experiment what we could do with some kind of model-based teaching. And by model, I mean having a model of the learner. And the idea is that if we could predict when the learner will be forgetting a word, then probably one could present words, one could present this word at the optimal time for the learner to remember it. So this actually, to implement this idea, we need to develop 3 components. The first component is the model of the memorization. So this model is here to describe how the learner memorizes. And then we need an inference algorithm, because this model of the memorization, it has some parameters that needs to be learned, and they need to be learned online during the interaction with the learner. And the third component that we need to develop is a planning algorithm, and this planning algorithm is just here to determine which what is the optimal presentation order for the words. Okay, so we developed a very elementary implementation of these 3 components. So that was more for proof of concept, and actually, spoiler, we reached the performances of Lightner system with this elementary model. So that's really cool. Okay, so for the memorization, we just decided to have simple exponential forgetting model. So all the cognitive among you are now extremely worried that it's not a realistic model. True, it's not, and it does not account for a very subtle things. But for now, as I said, it's supposed to be an elementary model, just for the proof of concept. And so exponential forgetting means that the probability that a word is actually remembered decreases exponentially over time. So when you just encounter the word, obviously you have probability 1 to remember, to have remembered it, but when you wait for 1 year, then the probability decreases to 0. And so here, this model have two little parameters. The first one, the alpha, is a base learning rate. So it simply indicates how quickly originally the user will forget about the word. So the first time they see, how quickly they will forget it. And then we have a memorization capacity, which affects the fact that after each repetition of the word, you will forget it less quickly. So if you have encountered the word, if you have revised this word 15 times, obviously you will forget it more quickly, less quickly than after the first encounter with this word. Okay, so that's That's a very elementary memorization model. Now they say it depends on two parameters, alpha and beta. These parameters, they must be inferred online during the interaction with the learner. Okay, so what is this interaction? This interaction is actually a sequence of words, W, and a result given by the learner that are right here, Y. Y in this context is simply a Boolean value indicated whether the learner memorized it or did not memorize it. We could have more subtle approaches, like for instance, if the answer of the learner is almost almost correct, but just made a mistake on one letter, obviously the learner has memorized it a bit more than if the learner has given something completely different, obviously. But again, this is an elementary proof of concept, so we do not take these kind of things into account. So here it just user learner had right or learner was wrong. Okay, and now we have strong constraints for the inference. These constraints are that we need to learn from a very limited amount of data. This amount is basically only the interactions we had, which are not a lot. And also the inference must be very quick, because it has to run in real time. Otherwise, you just cannot use your Duolingo. Okay, and one remark here is that the parameters alpha and beta, depending on what you want, they can be global for the learner and the item. So it means that whatever learner, for one learner, all items will be associated to the same alpha and beta. So all words will be associated to the alpha and beta, which means that the learner will have the same forgetting of all possible words. Or obviously you can also say that alpha and beta, they are specific to the user and to a word. So you have one alpha and beta for remembering the word dog, for memorizing the word cat, etc. And in this second case, this is extremely difficult, because then not only you have not many interaction, but you have really very few observations for each word, because for instance when learning vocabulary, you not expect to revise a word more than, I don't know, 10 times, and 10 observations in terms of doing inference, this is really few. Okay, so the way we do that is simply using a Bayesian belief update, and the prior we use for that is taken from the previous interactions. So this is rather simple. In practice, for the initial priors, we obtained them from a pilot study based on, I think, something like 15 users learning kanjis. So we could have we could get a nice distribution, a nice prior distribution of the alpha and beta. And second point is that to make this quick, we discretized the parameter space into a grid of parameters. And obviously now the time complexity for the inference depends on the size of the grid. So we have now to decide whether having a fine, a very thin grid, in which case we have big precision in terms of the inference, but it takes longer, or we can have larger grid, in which case we have less precision in terms of the parameter, but it's quicker. Okay. So now I have described only the model and the inference, but now let's go to the main, to the core question of how to choose which words to present. So the planning here, just a side remark, the planning is extremely difficult because we are in the worst possible case. We have a very large number of possible actions, so each action being choosing one word. So we have lots of words to present. We have a huge state space. So the state space is basically in which possible state is the memory of the user. So now we need we have actually something continuous. So that's really dramatically painful. And also we have a large horizon. So we are planning over maybe 1 week of interaction with the user, and that's huge. So we are in the worst possible scenario in terms of planning. So that's why we had to make a simplification. So the first one we decided is to have simply a myopic teacher, so a greedy teacher, which just presents the words that are getting forgotten at the right at this precise time. So that's actually this teacher is not planning at all. It's just checking. Oh, right now I think the user is forgetting about the word dog, so let us just give it the word dog. So no planning, but simple to implement. Okay. Then we had another variant, which we call the conservative teacher. So it's basically, so let's not enter into details, but it's basically planning, but like with limitations. And this conservative teacher is aiming like to guarantee that at each step, we are sure that the learner will have memorized, will not forget about the seen words. So if you have seen 10 words, you introduce an 11th word only if you can make sure that the user will not will be able to memorize the 11 words at the end of the teaching sequence. And so that's basically the gist of this conservative teacher. Okay. As for the results we obtained with this, in first experiment, we tested it with some artificial learners. So we simulated 100 learners and a teacher suggesting among 500 words. And the teaching, it will be the same for the user experiment. So it's organized in 6 sessions. Every day at a precise time, the users had to log in and have a session of 100 words. And at the end of the week, on the 7th session, they had a final test. So asking them for the words they have memorized. Okay, and so we tested our two teachers, so the myopic teacher and the conservative teacher, against the Lightner system, so the state of the art, and we evaluated it in terms of 2 metrics. The first one is the number of words that are actually learned at the end of the process. So that's basically the result of the exam. And the second metric is the ratio of the words which has been learned over the words which has been seen during the learning process. Okay, and so here are the results. So on the left-hand side, it's the number of words memorized, and here again. Okay, let's forget about. Okay, let's move to this experiment, which is more interesting. So on the left-hand side, we have the number of words that are known by the learner at the end of the learning process. And so we can see here that our 2 teachers, the myopic and the conservative teachers, are slightly better than the learner. Than the Lightner system, sorry, and that the myopic teacher yields much better results. Like you can have like twice as many words remember at the end of the process. However, what we observe on the right-hand side in the ratio between the word that has been memorized over the words that have been seen is that the Lightner and conservative teachers both, they guarantee that that when you encounter a word during your teaching, at the end you probably remember it. While the myopic teacher is a bit more violent, and that we observed also with the user study. So the myopic teacher is actually presenting lots and lots and lots of words and expecting you to, at the end, memorize some. So that's like the crudest way you could teach. You just overload your student with some words to remember, and at the end you say, okay, I presented him 100, so at the end he will have memorized 20, right? But that's absolutely not pleasant for the learners. Okay, and so we run exactly the same experiment on real humans. So we run it on 53 learners, and we had actually at the beginning we had 65, but 12 left, and I will explain why they left. And the task is learning Japanese kanjis, exactly the same organization, 6 sessions of 100 words, and a final test at the end of the 7th session. And for comparison of the teachers, we assigned each learner 2 teachers. So it's mixed experimental design, and the teachers. Each learner was being taught by the Lightner system at least, but also either the myopic or the conservative teacher. And so what we observe, okay, so on the left-hand side, the 2 figures are here to show the comparison between Lightner and myopic. And what we observe here is that myopic, indeed, as in the simulations, myopic have better, have in general a larger number of words memorized at the end compared to the Lightner teacher. But this is done at the price of presenting too many words to the user. So in the right, okay, left-right figure. Can you see my cursor? Okay, great. So on this one figure here, you can see that indeed, the myopic teacher makes the user memorize only half of the word which has been presented. And now it's time to mention these 12 people who left. Actually, the 12 people who left, most of them were attributed the myopic teacher. And so now this is like, okay, this is just, this is not funded observation. Unfortunately, we have had no interaction with them to confirm this. But we tend to think this was just before, because the myopic teacher is a horrible teacher in practice, extremely frustrating. And now for the conservative sampler, actually what we can observe is that we are like, we have average results which are similar to a Lightner one. We have a bit more variance, but this is basically the same kind of behavior, and same in terms of the ratio of learns memorized over learns seen. So that's very interesting, actually. So, you know, in machine learning today, there is this craziness about wanting to have better results, like beating the baselines, blah blah blah. Actually, here, on this aspect, we fail because we did not make better than the benchmark, but that's actually very positive result for us, because it shows that with a simplistic model we can reach the same kind of performances than the state-of-the-art method. And that's great, because actually compared to the Lightner system, we are way more flexible and we can adapt to many situations. And that will be what I will present in the second part of my talk in 5 minutes, maybe less. Okay, so coming back to the initial challenges, I mentioned the individualization of the teaching. And here in the model we presented, this individualization is guaranteed by individual parameters of the memorization model. So this is, we made it. As for the irregular learning sessions, this is taken into account by the planner, but right now not, because we just had fixed and known sessions. But like future works should for instance take into account like learns like the learning schedule of the learner. So for instance, does the learner come back to the application every second hour or every day, or yeah, so taking that into account. But this is not done right now. But this is an interesting problem if you want my opinion. And the third point, which is learning the learner's objective, this is not taken into account. And I will have a very short discussion at the very end of my presentation about this. Okay. Okay, what I missed? Wow, okay. I need to speed up a bit. Okay, now let's move to the second part, which is not about teaching vocabulary, but teaching grammar. And the question is, can we extend this work on vocabulary to grammar? And the answer, spoiler, is yes, but it needs adaptation. Because it is a similar but not identical problem. So, as I said, when teaching words, how we do it, we have a parameterized model of the memorization. We infer the model parameters, and we then plan to find the optimal sequence of words, guaranteeing the memorization. Okay, right? This is summary of what I said. Now, can we teach grammar the same way? And for this, I will take this running example of the inessive case in Finnish. So Finnish, for those who don't know, is a language spoken in Finland, and this is, I think, a language that has been created by the devil himself. Okay, and so when you open a book, a grammar book of Finnish, you will see that, okay, inessive case, this is simple. You just add SSA at the end of your word. Great. But no, this is a lie. Actually, in Finnish, they have 51 classes of nouns. And when I say 51, it does not account for some weird changes, like weird rules, which are called consonant gradation and vowel harmony. So in the end, you have this kind of transformation. For instance, yes, Stalo, it becomes Stalossa. You just add the SSA at the end. That's great. But Korpi, it's Korvessa. Like the PI became a VE. Why? Because Finnish. Rakkaus, then the final S transformed into a DE. So you have this kind of transformation, and that's a mess. And so, you cannot apply exactly the same, because you would need to to present every word one by one, and that's not how we memorize grammar. We do not memorize grammar by memorizing each case individually. We learn rules, and this kind of this rule learning thing is rather interesting because it shows our ability not only to memorize but also to reason about what we have. So let me illustrate this with simple examples. So always with inessive case in Finnish. So imagine that you have a learner, and the learner has memorized that koira transforms into koirassa and rakkaus into rakkaudessa. Then, okay, this learner faces one question, which is what is the inessive form of kissa? So to answer this question, first step, the learner will see that, oh, okay, probably that kissa is closer to koira than to rakkaus. And okay, I know how to transform a koira to get its inessive form. And then by analogy, here we are. I'm finally speaking of analogy. By analogy, we should be able to apply the same rule to kissa. And this answer is kissassa. And actually, this is correct. Wow. And here, I just noticed that this example does not bring any information, so I do not have to memorize it. The examples I had previously were enough to describe what I observe now with kissa. Okay, now second question. Now I'm asked, what is the inessive form of vieras? Same. Okay, vieras. Now I see that it's probably closer to rakkaus. Great. Then by analogy, I see that I probably need to replace the final S by a DESSA, right? And this gives the answer vieradessa. And actually, this answer is incorrect because the expected answer was vierassa. Okay, this is interesting because now I see that this brings information. So now I know that I will have to memorize this new transformation. So because I'm a mathematician by formation, I like writing this with X and Y's instead of examples. So now I just have a base of X1 transform into Y1 up to Xn transform into Yn, and I have a question: what is the transformation of X? So to answer this question, I first retrieve the xi's which are the closest to my x. Then I reuse what I know about xi, and this is basically analogy. So knowing that xi transforms into yi, I find the y hat such that x transforms into y hat. Good. And then I propose the answer, and I get the correct solution. And I decide whether to memorize this or not. So I adapt my memorized cases to account for this new observation. Sorry. And actually, this form of reasoning is well known and is called case-based reasoning. Okay. So, second. So now, my question is: can we use that to actually teach a learner who would use case-based reasoning? Because I haven't answered my question of how to teach grammar rules to human learners, and so actually let's use exactly the same the same procedure as for vocabulary. We must have a parameterized model of learning, but now this model is not memorization anymore. It's case-based reasoning, so it's a way more complicated model. And then we have parameters for this case-based reasoning. We have to infer them online and then find the optimal sequence of examples, blah, blah, blah. Okay, so exactly the same, except that instead of accounting for memorization only, now we account for memorization plus reasoning. And that makes the problem really, really challenging. Okay. So I said there are some parameters in CBR, right? There are some, and let me describe which are these parameters. So the first, major parameter, the one that you cannot avoid in any case, is the case base. So the case base is simply the collection of cases you have remembered. Okay, and so here it corresponds to what is like memorization status. Now we have also some domain knowledge. So the domain knowledge corresponds to some rules that are dictated by the domain, and these rules they will, for instance, constrain the search for a solution. An example of such a rule in this Finnish example is that in Finnish a word cannot end with SN. This is impossible. So this is an information that you must that you do take into account when you try to reason and to find a solution to a problem. There is also the similarity knowledge. So the similarity knowledge contains like all the factors used to assess the similarity between cases. And for instance, in Finnish, the last letter of a word. The last letters of a word are the most important when trying to find the similarity between the words, because like these are where you will add your suffix. So that's what matters in the word. Okay. Now there is also the adaptation knowledge. So the adaptation knowledge, it contains like all the information and rules that are used to the adaptation to new problems. So basically, this is about how people solve analogy. And an example in Finnish is vowel harmony. This is a very simple rule that the vowels A, O, and U cannot coexist with E, E, U within a same word. So that's not possible. And this actually guides, the way you you do the analogy. Okay, so so as a summary, we need to infer the content of the case-based, what are the parameters of case retention? So it means what are the parameters used for deciding whether you memorize or not a word? What are the parameters of a forgetting model? Then what are the background knowledge of domain constraints? What is the similarity measure that is used? What are the parameters of the similarity measure? What is the algorithm used for adaptation? What are the parameters of this algorithm? What are the rules in case we have the rule-based algorithm? So that's a lot. But but we can obviously have simplified models in which you just consider some of them, and I will show you that it's actually feasible to do this inference. So the inference itself, again, it's done using Bayesian belief update. The problem here, so okay, big math, woo. The problem here is that you have a very huge space of parameters. And this makes the inference extremely difficult if you consider joint parameter space. So it's not as clean, but the only solution we found was to marginalize and to simplify and to find only like okay, for each parameter, independently from the other, what is the probability of having the values for this parameter? So that's not as clean as we wanted, but this way we could make the inference. So it's not as clean, but at least it works. While the clean version does not work when you have more than 3 cases and and 2 similarity measures. Okay, now that's nice. I presented this example with the inessive. But that was very hand-waving. Now, if we want to code it, we need to have to implement this a CBR model for word inflection. And so this means that we need to define mathematically and like in terms of computer program each of these steps of the learning and reasoning process. So the retrieval, the adaptation, and the retain. So for this, we based on some previous work I had done in 2020 on morphological analogies. So okay, now guys, you have the analogies you wanted. So the idea is that in order to solve analogical equation Koira to Koirani as Kissa is to x, so in finding x here, we aim to find a function g on the words that such that g of Koira is Koirani and g of Kissa will be the x, right? The problem here is that there exists infinitely many such functions. So one obvious function is just adding ni at the end of the word. Yeah, works. But another could be you have your word, you add an n, and then you add the third letter of your word, right? Because Koira, the third letter was an I, and I added at the end an I. So maybe the final I in Koirani comes from the fact that the third letter in Koira is an I. Wow. Okay, I know this is definitely not the way we think, but this is a solution that works and that a computer will find when trying to explore. Another solution is just hard coding. The solution is just Koirani. Whatever word you ask me, I will answer Koirani. And of course, this makes sense. You can have very weird functions like saying, okay, you add ni at the end if the length of your word is less than 7 letters. Otherwise, you have other parameters. So yeah. Imagination is the only limit here. So how do we sort out from this huge number of candidate functions? Actually, we do that using a principle of complexity minimization. So for that, we proceed in 3 steps. First, we try to find a description language for the analogies on character strings. And then we code this language into binary strings. And in the end, we just solve the analogical equations by finding the function which has the shortest code using this representation. So, okay, this was a bit quick. Now I will illustrate it so that it's clear to you. Okay, huge slide, sorry. I will change a little bit the paradigm now. Previously, I said, okay, I will try to find G such as the analogy is A transform into G of A, C into G of C. Now I will just try to describe each domain using the function f. So I want to find f and some parameters x such that f of x describe A, B, and f of y describes CD in the analogy A is to B as C is to D. So f describes basically two terms at once. So in practice, the program I will write will have a first part which is defining the function f, then applying the function f on my source domain, so getting AB, and then applying the function f on my target domain, and blah blah blah. Some comments that are not interesting. Okay, let me be concrete. I want to describe the analogy able is to unable as known is to unknown. For that, I can say, okay, I define my function, so that's the first line, by saying I have a first argument. So here I write the argument with an interrogation mark and number of the argument. So argument 0, double dot, so here, transform into, and then concatenation of a u, of an n, and of parameter 0. Okay, so it just say that you take your parameter and you prefix it with un. Okay, and then you apply this function on the string able. So replacing interrogation mark 0 by able. So it returns indeed able transformed into unable, and then you apply it the same function to known. So that will be your target, and you have known transformed into unknown. Okay, that describes very well. So that's the simplest case. Now we can have more difficult functions. Like for this example, this is finish again. Vantut transform into vantu, and autopiloted transform into autopiloted. And here the function, as you see, is way more difficult. It's like you have your word, which is like your initial word. So for instance, vantut and autopiloted, you describe it by a first parameter, a second parameter, and a t, a final t. And then it transforms into the first parameter, a t, and a second parameter. Okay, and by choosing like the first parameters as van and the second in two, you indeed describe vantut transform into vantu. Okay, and same for autopilot. So that's basically the philosophy of like representing the source by one single function and the target by by the same function, but having different parameters. Okay, so then, okay, when I have this code, so it's nice, but it's written with letters. Now, as a computer scientist, I want to have zeros and ones, otherwise I'm not satisfied. So we transform this into zeros and ones using this. Okay, this has been chosen in a reasonable manner, but nothing very fancy here. Okay, and then okay, wow. I made this presentation, like this part of the presentation, to mathematicians, so that's why it's the mathematician way. But then now, the way I measure what I call the complexity of an analogy is simply so. I have, for instance, this code here for my function. I can transform it into a binary string, right? Using my binary code. So that's simple. And once I have that, actually, I just measure how many bits I have. That's all. So that's extremely simple, and this is called in theoretical computer science Kolmogorov complexity, because Kolmogorov is the mathematician who discovered this. Okay, what time is it? Whoa. Okay, I'm too talkative. Okay, so yes. So basically, actually, what we say here is the way we solve analogies is just, so we have A, B, C, A transform into B, C transform into Y. We must find the Y, and actually the way we find the Y is we take the Y, which minimizes the complexity. Okay, so this solution So it's well known in theoretical computer science, and we tested it for some Hofstadter analogies. So ABC transformed into ABD. So we made a simple user study to test that we humans use this kind of minimum complexity solutions, and actually the results were rather significant. That yes, we seem to have minimum complexity a way of solving analogies. So that's not completely out of my imagination. It makes sense. And actually, we also tested it on some analogies in different languages. And we reach our minimum complexity analogies. The first column here, so analogy comp, like complexity, and actually we reach extremely good results, and much better than some state-of-the-art techniques at the time, because now they are using deep learning, and it's it changes the problem. But actually, okay, if someone wants to ask me a question about why deep learning cheats here, I would be very glad to answer this question. But now I don't have time for that. Okay, so going back to my CBR model and trying to use this minimum complexity idea, how can we implement this in practice? So for the retrieval, so finding the case which is the closest to X, we came up with 3 possible distances, which basically, okay, for all the distances, just forget about the minus k of something. Just consider the first term. So the first distance is basically saying that a case AB seems very relevant to describe X. If you can, if the solution of the analogy AB XY is very short, it's very simple. Okay, distance 1 is almost the same thing, but we just change the normalization term. So the minus k is basically roughly a normalization term. It's just another normalization term. And the distance 2 here is just saying that we don't care about the B. We just check whether the A and the X are similar or not. So you can describe them in a simple way. Okay, so that's the 3 candidate distances that we could use for retrieval, and all of them make sense. And I know the intuition is maybe a bit difficult just on one slide, but I swear it makes sense. If you sit down and think, it makes sense. Okay, now for the adaptation. For the adaptation, we simply use the analogical, we simply solve the analogical equation using the minimum complexity principle that I described. Okay, so we have the algorithm already and it works. And for the adaptation, we just change it slightly by applying vowel harmony, in case the learner knows about vowel harmony, because solving the analogical equation will not account for vowel harmony. Okay, then we get the answer. And for the memorization, so here I plead guilty. That's a difficult part that we haven't treated yet. But for now, we just say we memorize it with a fixed probability. So that's not very realistic, but why not? Okay, and we try to check empirically if it's possible to estimate the parameters of this model. And so here we did not make a user study for this. So this is just on simulated users. But the principle is more, can we infer indeed the parameters of a case-based reasoning agent while interacting with them? And this is actually rather difficult and rather challenging. So even before making it more challenging and checking whether it works on human beings, we wanted to check that already it works on artificial agents. And so we implemented this this model that I described and interacted with them. So we have the user which has been exposed in the past to 100 cases. And among these 100 cases, they may have remembered some and forgotten some. And now the teacher aims to infer the user state. And for that, it will interact with them. And okay, and we make the assumption that the user does not change during the interaction. The learner is fixed now. We have 50 interactions with the learner, and within these 50 interactions, we aim to infer which are the cases the learner had remembered from the 100 cases, which distance they're using for the retrieval, and whether they do or do not know vowel harmony. Okay. We display the posterior distribution, the posterior probability of the parameters, and some score, which I don't want to describe. Okay, so, top figures. We have, the A is simply the probability, the posterior probability of each possible distance. And here, our user is implemented using distance D2. And as you can see, in about 10 steps, the learner was able to predict with probability almost 1 that the user was using distance D2. So this is a very good thing. Same for vowel harmony. Here, the user does not know vowel harmony, and it takes about 20 steps for the teacher to realize with probability 1 that the user does not understand vowel harmony. I need to say it again. Here we do everything together. So it's not solving each problem separately. Now we infer all this at the same time, simultaneously. And for the bottom figures, they are mostly about showing that we predict well the content of the case base, so the content of the memorized cases of the user. So that's very encouraging results. Other encouraging results, which I won't comment because I don't have time, is that we can do that also when the user is dynamic. So when the user memorizes during the interaction with the teacher. So that's really great. Okay, now let me conclude this presentation with some perspectives. So I will take 5 minutes more. Sorry. How, based on what I have presented, how can we make an even more general teacher? Okay, so there is a question that is very important, which is a question of the choice of the reward. This is something I completely avoided mentioning here. But this question comes from the fact that when doing the planning, etc., we have a mathematical formulation of the teaching, which is based on a partially observable Markov decision process. So for those who don't know, it's a very standard reinforcement learning framework, which is used a lot, for instance, in cognitive models. Basically, what this model describes what is the knowledge status of the learner, so the memorization of the learner. So that's what I have described the most in my presentation. Then there is the action space, so which are the teaching materials that the teacher can display. There is a reward, and the reward is what the teacher gains by teaching correctly. And so usually these rewards, they are like mathematical gain. It's not gain in terms of money or etc. But I will illustrate what I mean with this. And then there is a transition function, which is how the action of the teacher affects the knowledge status of the learner. Observation, which is what the learner responds, and the observation function, which is how the learner responds. So this is a model that has been developed by Ruffert in 2016 and corresponds roughly to what we want. Now the question of choosing a reward is critical in reinforcement learning, and because like you may be tempted to use a reward which is naive. For instance, here in Tetris, you would be tempted to say that that your reward is having a high score, ending the game with the highest score possible, with a malus when you end the game. Well, when you implement this reward, what happens is that the game will play Tetris very well. So it will maximize the reward, maximize. And when the game sees that it's about to lose, then it just pauses the game. This way, it does not get the final malus of losing the game, So it keeps being alive for infinite time, just on pause. Because when you said you want when you define your reward here in the naive way, then it does not correspond to what we would expect it. We would have expected, because we were expecting that the game accepts that it's losing at some point. Well, we have the same in teaching. The naive choice of a reward is a predicted score at the end of the teaching process. Wow, but actually, this has unexpected side effects, and this is combined with bad choice of a user memorization model. But what we observed with this naive choice is that the AI will just repeat the same words multiple times in a row. Okay, so in Finnish, dog is koira, dog is koira, dog is koira, dog is koira. Okay, I got it. Now please go to something else. So that's what we observe with this naive choice of reward. So how to correct that? By adding a strong negative reward when repeating previous action. That's not great. Or by modifying the memorization model. Here, saying that instant repetition does not bring memorization. And that's something we have modeled for that in cognitive science. Okay, other possible reward functions, the ratio of learned words over seen words makes sense. Then you force the AI to, to be sure that all the words that will be memorized, that will be seen, are memorized. But if you use this ratio only, it yields to unexpected behavior, which is that the AI will show you only one word. You will be presented these words hundreds of times. So at the end, you will have memorized this word, and you will have a perfect ratio. You will have memorized all the words you have encountered. Great. So definitely not something we want. So, lots of possible rewards are possible, but choosing the correct one is a really, really important and challenging problem. So I wanted to mention this. For inference issues, okay, let's just say that when we focused here in my presentation on teaching one learner. Now imagine that you have a teacher and you have 100 learners learning at the same time. Then you can exploit the information that some learners gives you to better teach the other learners. So for that, we could use a hierarchical model for the inference. So that's something we have. That's something we are currently working on. And more interesting, that will be my final words on learning sessions. So actually, the learning sessions affect the decision, as I said. So the learning is organized in learning sessions, and these learning sessions are of unknown date and duration. When they are known, which was the case in our examples, when they are known, they can be considered in the planning. But in practice, they depend mostly on the user. Then they depend on when the user has free time. For instance, maybe the user will learn in the bus when going to work. So it depends on the learner's learning habits. It depends also on how much time the learner has. Because sometimes you just want to have a very quick session revising 5 words and then going back to your life, or sometimes you just have 1 hour in front of you and you can exploit it. And also it depends on how long the user can study before getting tired, because obviously we are not machines and we get tired at some point. So as I said, there is this challenge of predicting how long the session will be and when the next session will be. But there is even more interesting. I said it depends on the user, yes, but it depends also on the actions of the teacher, because the actions of the teacher, they can affect the duration of the sessions. For instance, if the learner has a feeling to progress well, they will study more frequently. If the learner has a feeling that the teaching is too simple, they will get bored and they will stop studying. If the learner has a feeling that the teaching is too complex, they will get tired and desperate, and they will get rid of the teaching application. And for the last 2 points, there have been studied in cognitive sciences and on as zone of proximal development. So you have to choose material which is not too simple but not too complex. And now, why this is interesting? It is interesting because now I have described everything in terms of reinforcement learning, but this is actually a multi-agent reinforcement learning. This is a two-agent interaction where the teacher has an impact on the learner by making them learn and by showing that the teaching is useful, but the learner has also an impact on the teacher by requesting or discarding the use of the learner, so simply quitting the application. And that is something which is extremely interesting and extremely exciting, and I should find time to work on that, but unfortunately we have only 24 hours in a day, as we had only 60 minutes for this presentation, which I did not respect. This is the end of my presentation. So most of what I presented can be found in these 3 papers. So the first one is published in IUI conference and is about vocabulary learning. The second one is the part on case-based reasoning. It has been published in the conference on case-based reasoning. And the last one on minimal complexity analogies has been published in HKI in 2020. So that's all for me. So if you have any question, I will be delighted to answer.